All right, you guys, let's talk chemistry of the environment. Now you're going to have to bear with me because my tablet is not working the way that I want it to. So if my handwriting is trash, don't be mad at me. All right, here we go. This stuff is super duper important. Now we're not even going to get into the chemistry of the oceans, but we're going to strictly speak about the atmosphere in this lecture. And I know you guys all know about the impacts of global warming and climate change and how we're going to have to start curbing our CO2 emissions. And I know you guys are all talking about ways in which we can do that. But what I want to focus on here is like the actual chemistry of what's going on. Like, why is it that CO2 is a greenhouse gas? How is it that the ozone layer can be depleted and regenerated? So I want to talk the chemistry of this so that you can debunk any kooky things that you hear people saying out in society. All right, so here we go. Chemistry of the environment is really, really important because honestly, chemistry is at the heart of all progress and problems involved in our environment, I believe, right? Because everything's based on reactions. So chemistry is at the heart of all. See, why is my tablet doing that? It's just had enough. It wants to be done for the year like all of us. Of all problems, and luckily, all of the available solutions. Now, why are we talking about the atmosphere? We're talking about the atmosphere because the atmosphere is our first line of defense from radiation from the sun. See, what's going on here, guys? First line of defense from radiation. Lost my T. From the sun. Now, by radiation, of course, we're referring to electromagnetic radiation, right? So we are talking about energy that is quantized with specific frequencies and, of course, specific wavelengths. We're talking about any photons that are moving at the speed of light. And this radiation can have lots of different effects. Let's talk first a little bit about the anatomy of the atmosphere. As you can see here from this diagram, with temperature on our x-axis from low to high, and altitude, again, from low to high on the y-axis, we can see our atmosphere separated into 4 distinct spheres. The troposphere, from 0 to 10 kilometers, the stratosphere, from 10 to 50 kilometers, the mesosphere, from 50 to around 85, and beyond that, the thermosphere. If you're just trying to get like an idea of, well, how high up is 10 kilometers? 10 kilometers is about how high airplanes fly. It's about 33,000 feet. And so when you're flying in a commercial jet, you're flying right around the tropopause. Now, the reason why we say pause between these layers is because in these particular places where the temperature begins to change again, these areas, it's kind of harder for the gases that are distributed at this level to make it through to that next level. So that's why we call it the tropopause and the stratopause and the mesopause. And as you would imagine, the reason we have some temperature differentials in here, besides altitude, is because the gases are not distributed evenly throughout our atmosphere. And we'll talk more about the composition of these layers here in a minute. Let's take a look at temperature, though. What's interesting in the troposphere, and we're familiar with this because we travel within the troposphere, as we go up in altitude, temperature goes down. However, in the stratosphere, as you go up in altitude, the temperature goes up, and vice versa through the mesosphere and thermosphere. So this is interesting. So there's certainly a correlation between temperature and altitude, but it is not a directly proportional linear relationship. Okay, the other thing I want you guys to recognize about the atmosphere is what happens to pressure with altitude. And you can see here that our pressure in torr is on the x and altitude on the y. And as we go up in altitude, you see a very drastic decrease in atmospheric pressure. That's because gases have mass. And so due to gravity, at these lower altitudes, you're going to have much higher pressures. And very, very quickly as you move up into the atmosphere, you start to have fewer gases and thus lower pressures. So a couple of quick factoids here. Obviously, I want you guys to recognize that the pressure of the atmosphere goes down as altitude goes up due to gravity and mass. And let's talk composition of gases here for a second. Like when we talk about how quickly we lose pressure in the atmosphere as we go up, that's because 99.9% of all gas mass exists in the troposphere and the stratosphere. Up beyond that, you've got the rest of the gas, like 0.1% of the rest of the gases. So once you get past that 33,000 feet in elevation, you really start to pretty quickly lose gases, way less gases up here. And again, like I said, the composition of each of these parts of the atmosphere are not uniform or constant either. Down here in our troposphere, N2, nitrogen, and O2, which is oxygen, they make up about 99% of sea level gases. 99% of our sea level gases. Because you know there are lots of other gases besides nitrogen and oxygen here in our troposphere, but nitrogen and oxygen make up 99% of them. Let's take a look at this chart here on my PowerPoint to look at all of the other gases in the atmosphere. So we can see the mole fractions of the nitrogen and the oxygen. Again, this is near sea level. Those mole fractions are quite high, nitrogen being even much higher than oxygen's. And then the rest of these gases are, you can see some noble gases, as well as carbon dioxide and methane. These are our greenhouse gases. Nitrous oxide, which is a pollutant. And this is our general composition of the atmosphere. And you're like, well, why do I care? We care because of the reactions that are going to take place with these different compounds. All right. So let's talk about the reactions that produce things other than nitrogen and oxygen and the noble gases. So what we need to talk about next are photochemical reactions in the atmosphere. By a photochemical reaction, of course, I'm talking about a reaction that involves the absorption of a photon. And these photochemical reactions help to protect us from further radiation. Yeah, I should just start writing in cursive or something. From radiation. And we'll explain why. Okay, photodissociation is just like it sounds. If you dissociate a bond or break apart a covalent bond through the absorption of a photon, right? So photodissociation is the rupture of a chemical bond through the absorption of a photon. Now, when this happens, the electrons go back to their respective atoms. Like the shared electrons go back to their respective atoms. So no ions are formed. Everybody remains neutral. So here's a really important example that we're going to talk about a little bit later on. In the thermosphere, at around a little higher than 120 kilometers, which is in our thermosphere, there's something crazy happening. The oxygen that's up there is absorbing photons of light. Now, the way that we write photons of light, you guys, are just as h nu to indicate the quantized amount of energy of a particular photon. Why we don't say like E of photon, I don't know. But you're always going to see it written as h nu. So an oxygen atom, and we know oxygen, right, is this oxygen double bond, oxygen, with our lone pairs. I mean, at least my pen waited until the end to decide to stop working properly. Can you imagine if it was like this all year? Okay, so this double bond, if the wavelength of light is strong enough, in other words, if it's short enough wavelength, high enough frequency, high enough energy, can actually break this double bond. In fact, to break this double bond, you need 495 kilojoules of energy. And of course, we could plug that kilojoules of energy into our equation and solve for the frequency, and from the frequency solve for the wavelength. But I'll tell you right now, if I were to do all those calculations, I would find that the necessary wavelength, of course that's frequency in the equation, but we know that they're inversely proportional. The wavelength is around 242 nanometers required to break apart one oxygen bond. Now this 495 is kilojoules per mole, so of course you'd have to use Avogadro's number, blah, blah, blah. The point is you've done these calculations before. Okay, this wavelength, you guys, falls in the UV spectrum of our electromagnetic spectrum. I think I said spectrum and spectrum. The UV portion of our electromagnetic spectrum. So if that's the case, we can see that the energy that we're getting from the sun has the right wavelength to break apart this double bond in a photodissociation reaction. And so this oxygen is going to be left with 6 valence electrons, which again is for some reason a nightmare to draw. There we go, 1, 2, 3, 4, 5, 6. And another oxygen with 6 valence electrons. I mean, maybe if I put my pressure scale way up high, is that going to help? No? But way down low. I don't know, it never used to make that circle-y thing before, you guys. Can't do it. There, I'm just going to do little tiny dots. Okay, there are our lone pairs. 6 valence electrons, 6 valence electrons. And you're like, okay, Miss Rivera, I don't care. I don't care about those oxygens. Well, you know what? You are going to care about those oxygens because they're going to be important to us later. Anyway, the point is that this photodissociation reaction that's happening up in the thermosphere is absorbing a bunch of UV radiation. And that's good for us, right? So the O2 absorbs much of the high energy, short wavelength radiation that's coming in to our atmosphere. So that's useful, right? So it's useful for one thing in the sense that it absorbs some of this UV. And it's going to be useful for something else in a minute. But let's first talk photoionization. Think about what the difference would be. Photodissociation is we break apart into neutrally charged atoms. Photoionization is when the absorption has enough energy to just completely knock an electron off of the molecule. So this is when the molecule absorbs radiation and an electron is emitted, creating a cation, right? Because if we lose that electron, it now has positive charge. Well, if we're online in the fall, I think I'm going to need a new pen. Okay. All right, now actually, I think I had a slide here showing showing this first photodissociation reaction. Let's jump back to the PowerPoint here. Oh, nope. I'm giving away the secret. I'm not going to go there yet. Okay. So the reason why I said this reaction is important here, the reaction that breaks down diatomic oxygen into monatomic oxygen atoms, is because these guys are going to be really important in the production of the ozone layer. Now, I'm sure you guys have heard of the ozone layer before. The ozone layer is a shield created at the top of the stratosphere. This is a shield of, this is embarrassing, O3 at the stratopause. But how does it get there? I will show you, young children, how it gets there. This is pretty cool. Okay, so remember from our previous reaction, wavelengths that were shorter than 240 nanometers had the energy to break up O2 with a photon into O and O. Well, what about the wavelengths that are a little bit longer than 240 nanometers, but shorter than 310 nanometers? What can those wavelengths do? Because UV is not just 240. Like UV has a range. There's UVA, UVB, UVC. And so we don't want exposure to any of those wavelengths of UV radiation. So what are those wavelengths good for? Those wavelengths actually will serve a purpose for us by being absorbed by O3. Ozone can actually absorb those wavelengths of light. And so that is another protection against the radiation coming in from the atmosphere. But before we talk about that, I first have to look at well, how does the ozone layer even form? Well, here's what happens. These free oxygens that are just banging around everywhere in the atmosphere, they bang into another O2 that hasn't decomposed yet. So if you have a free oxygen plus an O2 molecule, those two things hit each other, and voila, you get O3, which is ozone. Maybe I should have put that up here. O3 is ozone. And then we said, remember, that O3 has the ability to absorb these wavelengths of light. That's why the ozone layer is really important, is it because it can absorb these other UV radiations. Well, what happens when that's the case? What happens when O3 is exposed to light? O3 breaks down into, can you guess it? O2 and another free oxygen, which is awesome because then that free oxygen can do a couple of things. That free oxygen can bang into an O2 and make more ozone so that the ozone layer doesn't get depleted. And additionally, that O could also just bang into another O and make more regular old oxygen gas that we need to breathe. And that is needed in order to produce free oxygens that go on to produce O3. It's like this beautiful, regenerating, recycling cycle. You guys, nature knows how to produce these renewable cycles. We should follow nature's lead more often. It's beautiful. So this production of O3 in the atmosphere, caused by the radiation from the sun, created the Earth's protective layer against too much radiation. I mean, it's pretty freaking cool, I think. I really hope my lecture's still recording. Sometimes I go through the whole lecture and I'm not even recording. Let's look. Yeah, as I'm still recording. Hopefully you're seeing what I want you to see. Okay, so back to my little image here that shows the creation of ozone. So here's our oxygen, hits some UV, breaks up into these singular atomic oxygens. Those atomic oxygens then go on to produce, when they hit an oxygen molecule, these O3 molecules. That's how we actually make ozone. I did not create an image for you showing how there's that beautiful cycle that continues to produce O2 and ozone. But we did show that here. Production of ozone, then ozone hits the light, makes O2 and more free oxygens. The free oxygens make more O2, or the free oxygens go on and make more ozone. Love it. Okay, but seeing as we are humans, we tend to mess things up. Now, it's not just humans that have messed up the atmosphere. There are things that are natural that can mess with what's going on with our atmosphere, like volcanic eruptions. But humans are playing a major, major role in what's going on in the atmosphere. And when we're talking about human effects on nature, we call those anthropogenic. Anthropogenic. Now I feel like I spelled that wrong. Did I? No, I guess that's right. Anthropogenic, you'll hear anthropogenic climate change, just means caused by humans. Well, one snazzy thing that the humans came up with back in like the late 1960s, early 1970s were these things called chlorofluorocarbons, or CFCs. These things were used as propellants, like in hairspray bottles, and you guys might know from some pictures of your parents, hairspray propellants in the 80s were a big deal. Lots of hairspray in the 80s. So hairspray propellants, any sort of aerosols like spray paint, any of those kinds of compounds used CFCs in their propellants, and they were also used as refrigerants. Yeah, the more cursive I write, the more it seems to accept it. So what are chlorofluorocarbons? There are two main ones. One is CFCl3, and the other is CF2Cl2. These were the two main CFCs that were being pumped out into the atmosphere a lot. They are very unreactive in the lower levels of the atmosphere. They're insoluble in water. All of which to say is they're tough to get rid of, you guys. If they're not soluble in water and if they're not reactive, they hang around as themselves for a really long time. And so as they move up into the upper levels of the atmosphere, seeing as they are gases, they are then subject to photodissociation reactions. So like what's going on when these chlorofluorocarbons end up at the higher levels of the atmosphere? So here's what happens. At around 30 kilometers in altitude, where the ozone layer exists, where O3 is quite abundant, scientists found out that these CFCs were pretty reactive to photons of light. So let's look at what happened to CF2Cl2. When it was exposed to a photon, it photodissociated into CF2Cl plus Cl. That chlorine, that free chlorine, then bonded with ozone, right? Because it was in the portion of the atmosphere where we have the ozone layer. This reactive chlorine reacts with the ozone to produce ClO and O2. And you're like, what's the problem? The problem is O3 is a reactant, and I don't see it being produced anywhere, which means we are going to deplete the amount of ozone at the top of the stratosphere. And that's a problem. It's a problem because, back up here, the ozone is absorbing this UV radiation. And if that ozone layer is not there, we're going to get increased levels of UV radiation. So, let's talk a little bit more about the effects of this. This is a second-order rate law for this reaction. In other words, this reaction depends on the concentration of chlorine and of oxygen. And by the way, it has a big K value, right? So this reaction happens very quickly. And so, you know, if you're in a place with a high presence of O3 or a high presence of chlorine, which you're getting from this photodissociation of the CFC, this reaction is going to speed up. And even worse, ClO, you guys, ClO itself reacts with light and breaks down into Cl and O, which means we're making even more chlorine, which is going to eat up any other O3 that there is. It's like this vicious cycle. Now, I'd like you to see, I'm going to show you how all of these reactions add up, okay? Because oftentimes you're going to see the depletion of the ozone layer written simply as 2O3 depletes into 3O2. And you're like, how? You're telling me about these CFCs and stuff. I don't see any CFCs in this reaction. And that might be one of those things that like you're actually trying to explain to one of your classmates when they say, oh, that's just a bunch of hogwash about CFCs being bad for the environment. I don't see any CFCs in this reaction. It looks like it just decomposes into oxygen naturally. There's nothing we can do about it. It's not true. This is the Hess's law overall reaction. This reaction is catalyzed by chlorine, and that chlorine is coming from the CFCs. So here we go. Let's Hess's law it. Let's say you have 2 chlorine atoms from the decomposition of 2 of those CFCs. Those 2 chlorine atoms will then go on to hit 2 ozone molecules to make 2 ClO molecules and 2 oxygens. I know we could reduce that to all ones, but with Hess's law, you know how we have to multiply through by a coefficient sometimes. Okay, so remember, these are my chlorines from my CFCs that we're pumping out into the atmosphere in our hairspray. It hits the ozone in the ozone layer. It breaks apart into ClO and oxygen gas. And you're like, yay, oxygen gas. But uh-oh, no more ozone, and we need the ozone. Additionally, remember, this ClO thing is a problem. These 2 ClO molecules also photoreact into chlorines and oxygens. And remember how we said free oxygens can go on and hit each other to make more oxygen. All right, so let's add all these guys up. Do you guys, hey look, see how chlorine is present at the beginning and at the end? It's going to cancel. But remember, if something's present at the beginning and present at the end, it is a catalyst. So yeah, it's going to cancel out. And I've got these 2 oxygens canceling with those 2 oxygens. And my ClOs are canceling. And there you have it. I've got 2 O3 molecules becoming 3 O2 molecules. But I needed chlorine to do it. This chlorine catalyst made this reaction happen. It's the fault of the CFCs. And so now we can go take a look at those slides here and see what the problem is. So what you guys see here is in like the late 1990s, we had really, really high levels of CFCs in our atmosphere. And that led to the depletion of the ozone layer. There was a big, huge hole in the ozone layer, specifically at the poles. And that, again, has to do with temperature and weather patterns, etc., why that was the most vulnerable portion. That's where most of the CFCs ended up. What happened in the late 1990s, 1987 and 1992, was limiting the use of CFCs by the United States government, and you can see some other governments across the world as well, agreed to lower their CFCs. Ours was called the Clean Air Act. What other countries called their agreements, we don't know. Well, we do know, but I don't know. I didn't go look it up. So what you notice happening here is these massive drops in CFCs in the environment. And I want you guys to hear these things and be hopeful, because with global action and government initiatives, we can change and fix these things. Like, these are fixable problems. And you're going to see how we fixed the ozone layer problem. It just takes the will of a people and some governments working together to make agreements. And you can bring up the conversations about, oh, but it's too expensive, it's too this, it's too that. Governments subsidize things to make them affordable all the time. The reason why gas can be pumped into your car at a reasonable price is because gas is subsidized. They have massive tax breaks and loans from the US government and from governments around the world to make it affordable. Imagine if we start putting those subsidies into renewable sources. Imagine if, like we did back in the 90s and the Clean Air Act came about, if we put money into finding replacement chemicals for CFCs, because that's what they did. And the CFC levels plummeted. And the ozone layer healed itself. So you can see here in this graph, these were where the ozone layer was the thickest, highest levels. And in the 1990s, when we had tons and tons and tons of chlorofluorocarbons in the atmosphere, excuse me, it took me a while to think of the word I was looking for, the ozone layer was quite thin. But it's been steadily climbing back up ever since those government initiatives. So I think that's pretty hopeful. Let's watch a quick little video about this.
Every day, as the sun shines on the Earth, it sends ultraviolet rays that can cause sunburn and sometimes damage our DNA. Like a sunscreen for our planet, the ozone layer absorbs most of this harmful radiation and protects us. But in the early 1980s, scientists discovered that the ozone layer was thinning over Antarctica each August and September. In 1987, nations around the world came together to fix the problem through the Montreal Protocol. The international treaty banned the production of ozone-depleting chemicals like chlorofluorocarbons, or CFCs. But these chemicals had been in use for decades, and they stay in the atmosphere for a long time. So, it took a while to see the effects of the ban. In 2000, the ozone hole was the largest ever observed by scientists. But conditions slowly improved. Data from NASA and several partners show a 20% decrease in ozone depletion during August and September from 2005 to 2016. In 2017, the hole is the smallest since 1988. A year later, the hole was smaller than expected. Studies suggest that the ozone layer over Antarctica should mostly recover by the middle of the 21st century.
So that is some good news. Okay. Now, on to talking about CO2 and its effect on climate. Greenhouse gases. All right. Now, when we talk about greenhouse gases, I first want to talk about what is the greenhouse effect at all? You probably saw this back in middle school, right? The greenhouse effect is, okay, well, the sun is emitting all sorts of radiation. Mostly the ones that are making it to us that are most harmful are UV radiation. This solar radiation makes it into the atmosphere. Some of it gets bounced back by reflection, either off of, clouds and some gases in the atmosphere, as well as bouncing off the surface of the Earth. Some of this obviously gets absorbed into the Earth and keeps the surface of the Earth warm. The Earth also emits its own radiation. The Earth, as the UV is bouncing back out of our atmosphere, as well as radiant heat from the surface of the Earth, is emitted as infrared radiation. Some of this infrared radiation escapes, but a lot of it is absorbed by greenhouse gases. We'll talk about how that happens in a little bit. These greenhouse gases are water, carbon dioxide, as well as some that are less abundant, but oftentimes, in fact, more potent in terms of how much heat they can trap in the atmosphere would be an example like methane. And we can't do anything about the water, right? We need the water in our atmosphere and we need water cycles. Water is a great example to think about as a greenhouse gas because if you think about a really dry place that doesn't have a lot of water in the atmosphere, like the desert, during the day, the desert is really hot because of all of that, UV coming in, all of that solar radiation, as well as all of that IR emission. It's really, really hot during the day in the desert. But at night, it can be absolutely freezing. And that's because there's not a lot of humidity or water vapor in the air to trap and hold that IR radiation as thermal energy. Places that are more mild and don't cool off at night would be your really hot but humid places like Florida and Georgia along the southeast coast of the United States. Really hot and humid places where you've got a lot of water vapor in the air, so it absorbs all of that energy during the day, and that water vapor can hold it at night, and so it doesn't get cold like the desert does. So where you have places with higher levels of greenhouse gases, you're going to have warmer atmospheres. And again, like I said, there's nothing we can do about the water. And honestly, we want the water vapor and we want the CO2, right? We breathe the CO2 out. The plants need it and need to breathe it in order to make oxygen for us. The CO2 is essential as well. But what has happened is mankind has vastly increased its amounts of CO2 in the atmosphere. Let's take a look at a couple graphs. The first thing that I want you guys to recognize, and this is oftentimes something that people out in society get confused about, is that carbon dioxide levels and temperature are linked. Absolutely, 100% linked. When you have high levels of CO2, your temperature is warmer. So you can see here our dark line is CO2 and our light line is temperature. So when the CO2 levels go up, so does the temperature. CO2 levels go down, so does the temperature. Up, down, etc. Now this is over the course of thousands of years, right? So we have data on this, you guys, for thousands of years that they get from measuring these levels of the ice cores, the thickness of the ice, as well as the amount of CO2 trapped in the ice. And we can see that even today when we measure temperature conditions and CO2 levels in the atmosphere at the Mauna Loa Labs in Hawaii, which is currently where the United States tracks all of its average CO2 levels and temperatures. With an increase in CO2, you get an increase in temperature. And here it is. Yes, this is the Mauna Loa graph I wanted to show you guys. So you can see the CO2 emissions throughout the course of the year. They go up, they go down, they go up, they don't go down. Like there's this, I'm pointing as if you guys can see me. There's this wavy effect of going up and down. That's just due to seasons, right? And with the seasons come high pressure and low pressure fronts, hotter and colder temperatures. And of course, the CO2 amounts or concentrations will vary with the seasons. So of course you get this up and down, just like we do with temperature throughout the course of a season. But what I want you guys to recognize is that these CO2 levels since 1960, when we started all driving vehicles of our own, these CO2 levels started to climb. Okay? And so if we know, going back to this graph, that if the CO2 levels are going up, the temperature levels are going up as well. And that is in fact what we are seeing. Now, this graph is showing, many, many thousands of years, because oftentimes people will argue with you and they'll say, well, there were ice ages and there was this and there was that. There's all sorts of things that account for changes in climate and changes in weather. What we're telling you is that CO2 and temperature are inextricably linked, going back millennia. And the thing that's changing right now is how much CO2 humans are putting out into the atmosphere. So like this graph didn't go far enough out to show you how high this peak continues up. This graph does. So these are levels of CO2 in the atmosphere, and yes, they do fluctuate naturally, okay? But in the course of these hundreds of thousands of years, is there any fluctuation that happened naturally that landed us at 400 parts per million? And the answer to that is no. So don't let your crazy uncle try to tell you that what's happening now is normal and just part of a normal cycle of climate. It's not. Okay, and so with these massive rises in CO2, we would expect to see massive rises in temperature, and that is in fact what we're seeing. And the goal of the Paris Climate Agreement that the United States needs to get itself signed back into is to make sure that the temperature doesn't change by another 2 degrees Celsius. Because you guys then know what happens with increases in temperature. We get the ocean acidification, we get the loss of coastlines, we get massive droughts and fires, massive famines and human migrations as coastlines and places to live are no longer habitable. other places no longer habitable due to the droughts and the fires and the famines that I was describing before. Climate is a national security emergency. If we want to be sure that the United States remains safe, secure, and peaceful, and if we want safety, security, and peace for the rest of the world, we have to solve the climate crisis. Okay, so here we go. CO2 and temperature are linked. CO2 changes over the millennia, but has never changed like it's changing now. And that's because of us. And we can see that specific rise right here in parts per million as the years go by from 1960 until today. We're still rising. Here's another graph that looks at CO2 emissions and temperature. Notice right around here in the 1960s. Now these are deviations from average. So like the deviations from average up until the 1960s deviated colder than average. And post 1960s, the deviations have always deviated hotter than average. So these red ones are hotter than average temperatures. And what do you notice right here is our gray line of CO2 emissions. It's undeniable. Now, where are we getting all of these greenhouse gases? Actually, you know what? Before we look at any more charts, let's answer the real chemistry scientific question of like, how the heck does carbon dioxide absorb heat? Like what's special about CO2 and what's special about water that allow them to actually absorb heat as they do? And what's going on here is that the IR radiation coming off of the Earth has wavelengths around, oh shoot, you guys, I don't think I wrote down my IR wavelengths. Did I? Let's just Google it real quick. IR wavelength. No, that's visible. Nanometers. Oh, right, because it's right at the end of our vis spectrum. Yeah, so like 780 nanometers. There we go. So from anything greater than 780 nanometers to probably, I want to say it's probably around 1,000 nanometers. Like if we're looking at our whole spectrum here, like this is vis, this is UV, this is our high end, and this is IR. This is our lower energy end, our longer wavelengths. Okay, so anywhere from sort of 780 longer is our IR radiation. These wavelengths in here are the perfect wavelengths that can actually change the vibrational frequency of a carbon dioxide molecule. Everything's quantized, right, you guys? Like these bonds have a certain amount of energy and they have a certain vibrational frequency. Now, normally a carbon dioxide molecule is linear and non-polar. Well, when it absorbs energy, it's going to change its vibrations, and there's 3 ways for that to happen. One is called a systemic stretch or a systemic vibration. Oh, not why am I saying systemic? Asymmetric. Ay. Symmetric and asymmetric. It's really late at night, you guys. Okay. An asymmetric stretch is when this bond ends up getting a little bit shorter and the carbon and the oxygen on this side end up coming closer together. See those shaded areas are coming a little closer together. These two atoms are now vibrating a little bit closer together, and the carbon and the oxygen over here are now vibrating a little bit farther apart. That's going to make this once symmetrical molecule polar. So I'm going to change the dipole on this molecule. All of a sudden, I'm going to get a dipole. The other thing that could happen is we could get bending of the molecule, where the molecule was straight, but when it absorbs this energy from the IR radiation coming off of the Earth, if this molecule starts to bend, I'm also going to get a dipole moment as well, because it's no longer this symmetrical molecule where the polarity of the bonds cancel. So I'm going to get a dipole here, and I'm going to get a dipole here with asymmetric and bending vibrations. If you get symmetric stretching, where this oxygen just goes a little farther away and this oxygen just goes a little farther away, this type of change to vibrational frequency is not going to give the molecule a dipole moment. So really, it's these two changes in vibrational energy that are going to allow the CO2 to absorb the IR radiation. So CO2 molecules absorb IR radiation and change their vibrations. They are now vibrating with a higher amount of energy, right? Because they absorbed energy. So they went from a low energy state, they absorbed that energy, and now they are vibrating with a higher amount of energy. This higher amount of energy is felt in the atmosphere as heat, as thermal energy. So because of the nature of the CO2 molecule as well as the water molecule, any molecule that has the matching or correct vibrational frequency to the IR radiation that's being emitted off the surface of the Earth has the ability to actually absorb that energy and trap it. And it won't make its way out of the atmosphere. It gets trapped in this absorption. So if we go back to our greenhouse gas effect here, if I start pumping in to the atmosphere lots more CO2, all of this IR radiation that would find its way out is not going to find its way out. It's going to hit these CO2 molecules, change their vibration, increase their kinetic energy, and this whole portion of the atmosphere is going to get warmer. So if people are like, I don't understand why a gas traps radiation, that's all it is. It's about quantized vibrational energies. I know it sounds a little more complicated, doesn't it? But it's not. Okay. And you might be saying, okay, Mr. Rivera, like how much CO2? I don't believe you that like we're putting out that much CO2. All I do is drive my car. Let's do a little stoic calculation right here, shall we? If you burn 1 tank of fuel in your car, and the fuel in your car, if you're driving a standard vehicle, is mostly octane. Okay, so C8H18. And you're burning it. O2. You know you're putting out CO2 and H2O. Oh my gosh, you guys, I don't even have a calculator up here. Let's balance this reaction with 8, 9, 25 oxygens, so 12.5. All right, question is, if I burn 1 tank of fuel, all right, my fuel tank is like 16 gallons of octane. If I burn 1 tank of fuel, how much CO2 am I putting out into the atmosphere? How much? How many pounds? Can't be that much. Let's do the stoic. 1 mole of C8H18. Gosh, I'm gonna have to use my calculator on my computer. Where is my calculator even on my computer? I can have one. Unbelievable. I think I have a fancy one. All right, don't judge me. My desktop is a mess. Oh, look how messy my desktop is, you guys. I was downloading a bunch of stuff. I don't even see my I don't even see my calculator. I downloaded a fancy calculator app. Oh, nothing. Is my phone here? Where's my phone, you guys? Oh, search. Calculator. There it is. Good grief. That took a lot longer than was necessary. What am I calculating? Molar mass. 8 times. Nope. 8 times 12. Plus 18. 114. All right, there's my molar mass. 114 grams. Mole ratio. 1 mole, C8, H18. 8 moles, CO2. You guys, look what I just did. I tried to convert gallons into moles using grams. Holy cow, who was going to stop me? Goodness. I got to do way more work. 16 gallons. I need to turn gallons into liters. 1 gallon is 3.79 liters. And then I can use the density. What's the density of octane? 0.702 grams per milliliter, which is 0.001 liters. Oof, now I can use molar mass. Good grief. All right, back to my molar mass of CO2. 1 mole of CO2, 44 grams. We want to turn that into pounds. 1 pound of CO2 is 454 grams. All right, here we go, folks. Now I gotta find my calculator again. Okay. We are gonna multiply the 16 gallons times the 3.79 liters in a gallon times the 0.702 times the 8 times the 44. All right, now we're going to divide by our denominators. We're going to divide by 0.001 liters. And we're going to divide by 114 grams. And we're going to divide by 454. Holy cow, you guys, 290. When I drive my car and I run out of gas, I have put out 290 pounds of CO2 out into the atmosphere. So, like, maybe we should be carpooling. Yeah? Annual global CO2 emissions are around 24 billion tons. Look at some graphs. Where does most of our emissions come from here in the United States? Well, you can see transportation and electricity. This is like what's going on in your homes, industry, agriculture, etc. Commercial and residence. That's more of your other things in your home besides the electricity that's pumping out everywhere across the country. So, like, where can you make the biggest difference? Transportation. If we all drove less, if we all drove electric or hybrid vehicles, if we carpooled, if we took one less plane ride a year, honestly, the planes are really problematic. If you turn off your lights when you leave a room, if you make sure you change out all of your old lights for LEDs, lots of ways that we can make simple changes at home. In terms of where are we getting our fossil fuels from, you can see we are still continuing to increase uses of petroleum and natural gas. Coal is going down, which is really good. We'll talk about why in a second. And here are some non-fossil fuel sources here down at the bottom. I guess I shouldn't have quite labeled it all fossil fuels. We have this increase in nuclear as well as biomass, other renewables being wind and solar. We got to flip this grid, you guys. We got to stop subsidizing the fossil fuels. And we got to start subsidizing the hydroelectric, the solar, etc. Excuse me. I'm sorry. I'm closing in on 1 o'clock and my pen thing doesn't work, which makes me incapable of speaking like a normal human. Okay. CO2 emissions by country. Now, this is interesting too. Sometimes we get into these like boneheaded political arguments. So, who contributes the most CO2 emissions by country? China. And we're second. And after that is the entirety of the European Union together. And then India and Russia and Japan. Now, you might wonder, India is a very, very populous country, just like China's, right? So China is up here because they have so many people. India is not. And that's because India has not developed technologically the way that China has. So there are way less CO2 emissions by country. And one of the arguments that we're making here as we go into these international accords trying to come up with fair ways to curb carbon emissions is like, well, would it be fair for countries like China and the United States that have had a chance to go through their industrial revolutions to say to India, which is just beginning its true industrial revolution, hey, you can't do this? Like, is that fair? And so maybe there needs to be some sort of differences in terms of how these climate accords are negotiated between countries that have already had the opportunity to have their industrial revolutions, and yet were the major contributors of the anthropogenic climate change we're seeing today. And maybe we shouldn't be expecting those same kinds of curbs from countries that are less developed. Now, this chart is a little bit deceiving, right? Because it doesn't account for population. So let's look at population per capita. Per capita means per person in the United States. We are the worst. So when you hear certain people always blaming China for everything, how far down China is? In other words, per person, they're putting out way less CO2 than we are. So think about that. All of us greedy Americans driving our big fancy cars. Okay? All right, so you got to be careful when you're looking at graphs. You really need to look at all of the factors involved. Okay, let's finish off our conversation with the other things that are messing with our atmosphere. Carbon dioxide's not toxic, right? It's not messing with our atmosphere. It's just making it warmer. Well, I guess that's messing with it. It's not polluting our atmosphere. Just making it warmer. And you don't need all this fancy chemistry either, you guys. There are some really simple, great videos where they take these IR lights and they shine them on these two bottles, one that's full of CO2 and one that's full of oxygen, and the CO2 temperatures just skyrocket in the CO2 bottle as opposed to the pure oxygen bottle. So you can just see it for yourself. Other things that are contributing to problems in the atmosphere are sulfur compounds and nitrogen compounds. And we're going to talk the sulfur compounds first. The reason why I said it was good that coal was going down is coal has a lot of sulfur in it. And when we burn these sulfur-based compounds, sulfur dioxide, in oxygen, we get sulfur trioxide. So in coal burn. Sulfur trioxide, besides being a just a gross, black, smelly smoke that you don't want in your community. Oh, I misspoke earlier. It was not the Clean Air Act that got rid of the CFCs. They said it in the video. I think it was like the Montreal Agreement or something. The Clean Air Act was one of the factors in reducing sulfur emissions from coal burning power plants. Sorry about that. Okay, so back to what do these sulfur compounds do? Well, the sulfur trioxide reacts with Oh, I don't need a coefficient of a 2 out there. Sorry about that. The sulfur trioxide reacts with water to make H2SO4. And H2SO4, you guys, is sulfuric acid. And you're like, well, what's the problem? Well, do you really want sulfuric acid, one of the 7 strong acids, raining down on you? Oh, that's supposed to be rain. On you and your pools and your fish tanks and your ponds and your lakes and your rivers? Do you want acid rain? No. Because normal rain, you guys, just from the other stuff in the atmosphere, has a pH of around 5.6. Acid rain found in areas surrounding coal-fired power plants has a pH of 4, quite acidic. Can really cause some damage to living organisms, both us and the things in our water supplies. In our water supply that we would be drinking, as well as the fish and microorganisms that we need in the water. But, like I was saying, the Clean Air Act came along, some of which has been dismantled by the current administration, so be thinking about that as well. The Clean Air Act reduced the amount of sulfur dioxide in coal-fired power plants. Remember, that's the first part. The sulfur dioxide makes the sulfur trioxide by 40%. Now, you can actually remove some of the sulfur from the coal before you burn it. It's just more expensive. So are you going to be paying a little bit more for your energy costs? Yes. Are you going to be paying less in environmental cleanups? Yes. Are you going to be paying less in medical bills? Yes. So we want to be thinking about all of these things when we think about, oh, how expensive is this? And how important is business and the economy versus clean energy and a clean environment in which we can live? Okay. Lastly, besides what's going on with coal, back to my graph here. You can see where the acid rain is the most significant. Okay, so here with these low pH values, these are the areas in the country where we do what? Pennsylvania, Ohio, West Virginia. This is coal country, people, right? So a lot of hardworking Americans earning their livings by digging coal. But that coal then produces sulfur dioxide, which produces sulfur trioxide, which produces sulfuric acid and acid rain. Not to mention the fact that digging and mining for coal is an extraordinarily dangerous job and really hazardous to people's health. What if we could institute programs that retrained coal miners as hydroelectric engineers, as solar panel installers, as wind turbine installers and operators? It just takes will, you guys. We did it after the Great Depression. We can do it again. Okay. Lastly, nitrogen oxides and smog. One of the things that comes out the tailpipes of your car, oops, not what I want. One of the things that comes out the tailpipe of your car is nitrogen monoxide. So here's what happens in the combustion of some vehicles. Nitrogen in the air and oxygen in the air plus heat. Okay, so this is a byproduct of combustion. Produces nitrogen monoxide. Nitrogen monoxide then goes on to react with oxygen to produce nitrogen dioxide. This guy right there is smog. It's really dark in color. It has a bad smell. It's damaging to your respiratory tracts. It's not good. Smog is kind of gross. It's not good. And On really hot days, smog often gets worse because this reaction is actually endothermic. So when on a hot day, this reaction shifts to the right, makes more smog. Go over to our PowerPoint here. LA is a city known for a lot of smog. Salt Lake City is another city known for a lot of smog. So you don't want to be breathing that in. One of the things that we can do to avoid all of this smog is doing emissions tests on our vehicles. And when we started testing to make sure that our vehicles were not producing excess amounts of nitrogen monoxide, guess what happened? We got a really big reduction in these nitrogen oxides in our atmosphere. So again, I want you to see these graphs, you guys, and I want you to feel hopeful and powerful. But it takes action, and it takes lobbying. And if the lobbyists that have the most power are the energy industries and the car industries, we're going to have some trouble enacting the laws that are going to make it possible to fix this. So get out there and get to work in your communities. All right. So here's another really bad problem with smog, is another photoreactive reaction, which is NO2 absorbs photons of light to make more NO, so it sort of like feeds the feedback loop, and some free oxygens. Well, you know, free oxygens up at the upper level of the atmosphere isn't a problem, but free oxygens down at our level of the atmosphere, they bump into regular diatomic oxygens and they make ozone. And while ozone is good at the upper levels of our atmosphere as an ozone layer, ozone down by where we are here is not good because ozone is actually toxic, especially to people with respiratory problems like asthma. So there's a couple of reasons why we don't want these nitrogen oxygen compounds to be proliferated in our cities and towns. And so there you have it, you guys. Big overview of atmospheric environmental chemistry. And this, again, didn't even get into the water bit that Taylor talked about during her presentation so nicely. I hope you got something out of that. And I'll see you guys in class.